In this video, we will talk about energy in detail. And just to recap, in our earlier video, in the previous video, what we saw was how work and energy were two sides of the same coin, and how energy was transferred from one agent to the other through work, right? So we saw that the movement of the hand here. In this case, the hand was the agent. The work done by the hand transferred the energy to the cue stick, and the work done by the cue stick by its movement transferred the energy to the ball, and the ball ended up doing the work, which was about reaching the pocket. Now let's delve a little deeper into this energy. So this energy is called the energy that we took, that we considered in this example is called the mechanical energy. There are different forms of energy. There are different forms, and mechanical energy is one type or form, right? It's called mechanical because you acquire that energy through a mechanical process, which was like movement of your hand or movement of the cue stick or movement of the ball. It was a mechanical process that helped that agent acquire that energy, right? So it is mechanical energy. And even within that, even this is not complete. This mechanical energy, if you really observe, this object was in actually a motion, right? When it acquired that energy, this object was moving. In all the three scenarios, your hand was moving, and your which resulted in the movement of the cue stick, and which resulted in the movement of the ball. So, in fact, a more accurate way to quantify that energy is called it's called the kinetic energy. So, kinetic means motion. The energy that was acquired by virtue of motion is called the kinetic energy. So this is a more accurate way. It is mechanical energy, but to be more precise, you call that energy that you have acquired from motion as the kinetic energy. So in all the three cases, your hand acquired that kinetic energy by doing that work, and which was transferred. That kinetic energy was transferred into the cue stick, and the cue stick ended up the kinetic energy of the cue stick ended up moving, and ended up the ball having to do that work, right? So in all the cases, because we have said that your energy and work is actually the same. So the kinetic energy of let's say the cue stick, right? The kinetic energy acquired by the cue stick is nothing but the work done by the cue stick, right? So let's try to derive let's try to quantify what that kinetic energy would be. So the kinetic energy of the cue stick is equal to the work done by the cue stick. Which is equal to, so I'm going to derive this, and we just saw that the work done by the cue stick is going to be MC, AC, and the displacement, right? Now, if you notice this this formula, the D is actually the displacement, right, of that cue stick from this point to this point. And in fact, we know that from the Newton's, the three laws of motion, we knew that the third law of motion was this, right? So it was 2AS. Let me use a different color. From the three laws of motion, we saw that 2AS is equal to V squared minus U squared, and S is equal to V squared minus U squared by 2A, right? So in this case, S was the displacement, right, of an object that had an initial velocity of U and it reached a final velocity of V. The third law of motion was this one, right? This is all the three were related. the acceleration, the displacement, and the initial and the final velocities. So you can replace, yes, so here also, although we call it d, this is also displacement. So we can replace d with this value, and which means that you will have mc ac times v squared minus u squared by 2a. It is the acceleration of the q stick, so it can be 2ac, right? So in this case, you can cancel you can cancel AC in both ways, and you know that yeah. So this is the result. So this talks about the initial velocity of u and final velocity of v. But in this case, for the q stick, the initial velocity of the q stick was 0 because the q stick was at rest, right? So and then the work done ended up the q stick acquiring this velocity of v. So u is considered to be 0 here, right? Because the q stick was at rest before the work was done. So which means that this is equal to mc times v square by 2. Now this is the formula for the kinetic energy of a particular in any particular object. An object of mass c, an object of mass m, if it is moving with a velocity of v, by virtue of its motion, it has a kinetic energy of it has acquired a kinetic energy of half mv square, right? If m is considered to be the mass of that object. So this is a part of the mechanical energy of an object, which is the kinetic energy, and the kinetic energy is nothing but the energy that is acquired by an object by virtue of its motion, right? Now, why did I say that kinetic energy is only part of the mechanical energy of a particular object, right? We started with saying that this whole thing, this whole energy is a mechanical energy, and to be precise, we called it as kinetic energy because by virtue of motion, this is the energy that it acquired by virtue of motion. But there must be some other aspect. If I'm calling this to be a part of the mechanical energy of the object, there must be some aspect, some other aspect to it as well, right? So let's understand that. So this energy is this formula quantifies the energy of an object by virtue of its motion. Let's consider a scenario where you have an iron ball. I'll take this example. I'm going to use a different color. So I'm having an iron ball that is left hanging from the ceiling or somewhere, and that is at a certain height from the floor, right? I think it's a little slow here, but yeah, it will soon come up. So here I'm talking about a scenario of an iron ball. So this is an iron ball. Let's call the mass. Let this be let m be the mass of this iron ball, and this is hanging, right? This is hanging from the ceiling or someplace, and it is at a height of h meters from the ground, from the surface of the earth. Now, this object is not moving, right? This object is not moving. So the mechanical energy of this object is 0, or no, we cannot say that yet. But we know that the kinetic energy of this object is 0 because this ball is clearly not moving, right? And it is actually hanging, and it is at still. Now, what will happen if you cut this if you snap the string of this particular iron ball? Because this object is on the surface of the earth, which means that it is under the influence of Earth's gravity, right? When you snap this string, which means that this object will immediately fall towards the earth, right? So which means that this object will start to move, and it will cover a displacement of h, and it will hit the surface of the Earth, right? So which means that although the object is not moving, by just snapping it, the object will end up doing some work, right? Which means that although the object is at rest, this object holds a capacity to do some work. It has, in other words, this object, this iron ball, has the potential to do some work, although it is at rest. And that is because it is held at a height above the Earth, and the gravity gives this object, the force of gravity has given this object certain potential to do some work, right? If this iron ball was held here, if the iron ball was, held here, somewhere here on the ground, there is no potential because it is already, it is already on the ground. Consider there is no gap here between the iron ball and the ground. That there is no real, it cannot go any further, right? But when you lift it up, it acquires a potential to do some work, right? Which means that you can use this height to break something, break another object here, and do all sorts of things. So by virtue of moving an object away from the Earth, the object acquires that potential to do some additional work, and that's what we call as the potential energy. So potential energy is the object's capacity or the object's potential to do some work when it is at rest. So if you really consider this particular iron ball, and how do we quantify this potential energy? It will be what will be the eventual work that it will do when you snap this one. This object will start to move towards the Earth with a certain with a certain velocity, right? It will acquire it will go on to the influence of the Earth's gravity, which means that it will experience a force. And that force is going to be mg, right? M is the mass of this object and g is the gravitational force. And it is going to, if it is held at a height of h, then it will have to travel a height of h, right? So it is going to be mgh. So the potential energy of a particular object at rest is always mgh. And if h is 0, which means that in this case the object is on the ground, which means that h is 0. In that case, the potential energy is 0 because there is no real potential for it to do work. But here, once you lift it up, it acquires that potential energy, right? Which is mass times the gravitational acceleration times the height. So that's why I meant that the mechanical energy of a particular object is actually a sum of both the kinetic energy plus the potential energy of that particular object. So to summarize, your total mechanical energy is equal to the kinetic energy plus the potential energy of that particular agent. So this completes our discussion on the first form of energy, which is mechanical energy. But this is not the only form of energy. There are other forms of energy, and they are you have apart from mechanical energy. We have heat energy. These are some of them. We have heat energy. We have chemical energy. We have electric energy. We have light energy and few others. Right. We have light energy and few others. So mostly we are going to focus on mechanical energy, but there are other forms of energy as well. Now this might be a good point to a good moment to come back to this diagram of ours, wherein we were looking at the example of let me just move this to the middle, where we explored the idea of, how an agent, by virtue of doing work, was able to transfer the energy, right? Transfer the energy to another agent. So in this case, the movement of the hand, by virtue of the movement of the hand, the energy was transferred to the cue stick, and by the virtue of the cue stick doing some work, it ended up transferring that energy to the ball, and which ended up the ball doing that work, right? So we didn't see we did discuss that, it is the same energy that is transferred from the hand to the cue stick and to the ball. None of the agents created new energy; it just transferred, right? The hand transferred the energy to the cue stick. The cue stick transferred the energy to the ball. So which means that how did the hand acquire that energy in the first place, right? So if you really go back, if you really plot this up front, the hands acquired that energy because of the muscular movement, right? That is what helped the hand move. Your muscles inside your hand moved, and that is what made your hand move, right? So your muscular energy is there. Your muscular movement is what created that energy. I shouldn't use the word created that energy. I mean, your source of energy was the muscular movement inside, right? What is the source of that muscular movement? I'm still standing still, right? When you're hitting the cue stick, you wouldn't be moving, right? But your muscles moved inside you, and the source for that is possibly the energy that you gain from the food, right? So that is where your chemical energy from the food was possibly the source for your muscular movement. If you were completely drained if you hadn't eaten for a long time, obviously you would not be able to move. You would find it difficult to move your hand. You may not be able to move your hand, right? Which means that there is no real source from the chemicals, from the food, right? So in a sense, your source eventually comes down to a chemical energy from food that we consume, that helps us, the chemical energy from the food helps us, is transferred, has helped us move the muscles and let our muscles do that work. And by virtue of the muscles doing that work, we were able to move our hands. And by the virtue of the hands doing that movement, we ended up the cue stick moving as well. And because the cue stick was moved in the right direction, it ended up the ball being moved. So if you really observe this thing, you also you see that the energy. What you acquired as energy from the foot, right, is what is transferred all throughout. And if you notice here, this chemical energy is transformed into mechanical energy here, right? So the chemical energy from the foot is transformed into the mechanical energy through muscular movement, and then it stays as the mechanical energy all throughout. Now, this brings us to a point to understand an important aspect about energy. And you will see this aspect come in many different forms. We have already seen this in the laws of motion, which I'll quickly relate to. But what we're really seeing here is, the universal law of conservation of energy. The law of conservation of energy states that you can never in an isolated system. In an isolated system, which means that it is only me as a human and the cue stick and the table. There is no other external force here, which means that in that isolated system, energy can neither be created nor destroyed. It can only be transformed from one form to the other, which is precisely what we have articulated here. The chemical energy from the food inside me, I was able to transform that into into mechanical energy, which resulted as muscular movement, and then it got transformed into another. It got transferred to my hand, and then it got transferred to the cue stick, and then it got transferred to the ball, right? So the law of conservation of energy states that in an isolated system, energy can neither be created nor destroyed. It can only be transformed from one form to the other, just like how we have seen here, the chemical energy transform into the mechanical energy, right? So this is the law of conservation of energy. So just to recap, the law of conservation of energy states that in an isolated system, the energy can neither be created nor destroyed. It can only be transformed from one form to the other. And I said that you will find this law in many different places. We already saw that in this universal law of conservation. It will come under some form or the other, right, as we learn different aspects in physics. We already saw that in while we learned about motion, right? We saw that in the form of law of conservation of momentum, wherein there again, we talked about an isolated system and how the momentum of objects that were colliding is always conserved. The momentum before collision is always the same as the sum of the momentum after collision, right? So this law of conservation will come. We will go through this will come back to us in many different forms. What we learned in momentum, we just saw that with energy, and we are going to explore a few more as we learn about other topics in physics. So I hope we were able to get a fair handle on what work is and what energy is, and how these two are the same sides of the same coin. And we went through in detail and derived the formula for the two components of mechanical energy, which is kinetic energy and the potential energy, and also we saw the other different forms of energy. And then we just saw the universal law of the law of conservation of energy, which is about how energy can neither be created nor destroyed, but it can only be transformed from one form to the other. Right? So the one last thing that we will talk about is power. So power is nothing but the rate of doing work. So power is not as fundamental as energy and work. But it's a very useful concept that will come in handy when we solve practical problems. So power is nothing but the rate of doing work. So if there are two people, let's take the example of this cue stick. If there are two people, if one can move the cue stick, one can cover a distance of let's take 1 meter in 1 second, and another person can cover say 2 meters in the same second, which means the second person has more power, right? And which is nothing but we say that he or she has more power because he is able to do more work at the same time, right? So the rate of doing work is more. That's when we say that one particular agent or a person or an object has more power, and the rate of doing work is equal to the work done by time taken, right? By the time. So which is joules. So the unit for power is joules per second. And similarly, we have a shorthand for power. We don't call it joules per second. We call it watts. We call it in watts. So which is 1 joules per second is 1 watt. And this is because of this is in the honor of another physicist, James Watt. For all his contributions to physics, we attribute the unit of power to James Watt. So I think we have covered all the three ideas of work, energy, and power, and we saw that the unit for power for energy and work is in joules, and power is always measured in watts. And sometimes typically the quantities of joules are very high, so we typically measure them in kilojoules or in kilowatts. That's purely from a convenience standpoint, just to deal with manageable numbers, right? So we always one kilojoule is considered to be 1,000 joules, and 1 kilowatt is considered to be 1,000 watts. Right. So So we'll use these in some of the problems that we will soon solve. So we'll mostly deal with kilojoules and kilowatts because the numbers will, as we calculate the joules and the power and watts, we will find the numbers to be pretty huge. So just to manage the compact them, we'll refer to them as kilojoules and kilowatts. So I think with this we have come to the end of the conceptual view of work, energy, and power. And the next videos we will go through the in-text questions and also we'll also solve the problems as part of the extract section.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.